platform, in this case a microcontroller. So fortunately or unfortunately, because of the IP and everything else, there are different companies that make these microcontrollers, right? And you don't really, I'm not aware of any microcontroller these days that you can configure or write, let's say, natural language or whatever. So in other words, we reach out to these things not as a software, but really we configure the microcontroller. So I don't know how many of you had microcontroller class?
We've had embedded systems.
Embedded systems?
Yes.
With
Dr. Shu and Seth.
Okay, yeah, so he's very good. So I don't know how he teaches, but again, it can be theoretical, and then on the practical side, there are many different ways. As I said, my senior PhD students prefer to do their own codes, right? But that requires certain knowledge about coding. So still here you can do that. But basically there are a couple of functions that we have to understand. One, you're dealing with a digital processor, right? So your sensor board or what we have can measure here is basically an analog signal, right? So basically when you have analog signal and you have a digital processor, you need certain interfaces to make the analog signals to digital, right? And then the digital needs to go back to analog if needs to be controlled. So in that manner, for power electronics or perhaps for many applications, you have to basically have 4 modules in every firmware, right? So the first one is how can you manage the serial or any type of communications, right? So let's say your processor sitting here, you want to send a command to your physical setup, right? So imagine that you have a breaker, you want to turn this on or off, right? So enable a bigger system to operate. In this case, let's say a PV inverter. So you have to basically create or set up that communication channels. The second part, basically you can do that in any digital output. Basically you're trying to create a pulse. So for your gate signals, right? So the control is basically a series of pulses for your transistors to on and off. So imagine that you're creating the function generator, right, with your microcontroller. Basically, you have to define the phase, the period, and the duty cycle, right? And this is becoming so important in many applications that microcontroller guys decided to actually dedicate some specific channels that you can create a very precise, right, with highest accuracy of those signals. So those channels are called PWM or EPWM, like enhanced PWM. So it doesn't mean that you cannot create from other ports in this, but basically you have dedicated channels that is preferred. The third is basically how I can basically read my analog data, right? So in modern microcontroller these days, they have, again, some ports dedicated for analog reading. So it doesn't mean that it can process analog. Still you have a digital processor, but it has analog to digital interface or converters built into this module, right? So the third thing is, okay, what's the resolution of this conversion, right? And in analog, you measure that, like basically based on ripple, and in digital, the accuracy is go by the bits that we assign to a signal, right? So you can have 8 bits, 12 bits, 16 bits, and that defines your accuracy. The last part, which is required for your control, is basically at the end of the day, you saw that basically you measure some parameters, let's say electric current or voltage, then you do some math functions, let's say subtract, then you go to a compensator, right? So that compensator is nothing else than some gains and some more calculations. The output of that is basically your controller. So in other words, you have some algorithm, if you will, to do, and there are multiple ways to do that, but basically one way is basically do you need to synchronize that calculations to any important parameter in your system, and that usually defines, or the limitations is the frequency of EPWM channels or your converter. So let's say if you're controlling at 10 kilohertz or 20 kilohertz, how often you want to update the control output, right? So basically you're saying that, okay, I define my calculations, right, to a certain period, and then update the output, at certain rates, right? So that's basically what I define here as basically you don't have to turn in, but I recommend you to just go through it once. Basically this can be done individually. You don't need your team members to be present, right? But basically if you do these 4 modules that should not take more than 2 hours, basically you are done. You can use any type of microcontroller, right, that MATLAB supports, and basically make that function, create that environment. So we have 4 modules, right? For 5.1, right, basically you need 2 of these modules, so, or maybe only 1, right? So you may want to create the communication channels, and you want to basically generate a PWM signal, right? So for that, I just made that, so I quickly go through it. So basically, the first thing, if you open up your MATLAB, you see that the interface or the menu, I don't know if you just open your MATLAB, you see this hardware or not. I don't think so, right? You have to set it up, right? Yeah. So basically the way that it's set up is you just go to the configurations, right? How many of you have done this? Great. Yeah. So I don't know if you noticed that, or I put the note there. Do you have your files on the cloud synced into your desktop, or?
I had some weird problems with it. I had to save it to the documents because any of the places that it was stored in that had a space, it was showing no pathway.
Exactly. So this you may get stuck with it. So these days we usually sync our files from cloud to our laptop. So it looks like either you have to manually define the path, otherwise it doesn't understand. So wherever you save your, basically the drive that you save your MATLAB and TI should be in the same folder. It should not be on the cloud. So I use Google Drive, so it shouldn't be on your G drive. So I have it on my C drive. I changed the simulation, I don't know if I think we tested we can, but you have to change. Another thing is, we change it to fixed step overall, and define the fixed step, I think it's 1 microsecond or 5 microseconds. But in the hardware implementation, you just go to the hardware board, and then you see these are all the different platform that I think MATLAB can support, right? So that's the first thing that you know you want to know. You want to set. So I think yes.
Can you also do this like if you use MATLAB online?
No.
Or it has to be the one in the division?
Has to be local.
I don't know.
It doesn't work.
And then we download version.
I think you have
Yeah,
to do.
you can't do the
download
hardware.
add-ons.
Does you have to
Yeah.
add ons and stuff to that?
It doesn't have the COM ports.
That's unfortunate.
That's a good question. No, but this has to communicate.
Yeah.
Yeah.
Okay.
Yeah, that's another point.
Cause I said like MATLAB is not like working on my, I tried downloading like MATLAB on my computer for like a day and it's just not working. I can use the online version, but it ain't like download the.
Yeah. You guys have you downloaded it, right?
You know, this, do you have 2023 boot?
Yeah, it's like, I think I had 2023A and then when B came out, that's when I tried to like get that.
You use B.
Yeah, and it just won't, after that, I can't even go back to the link.
It just doesn't run
It's
after
not
he
working,
tried
it's
to
not
upgrade it.
working.
There's something glitch.
They tried to install it. Yeah, it's some weird issue.
I wonder if there's like a MATLAB cleaner, like there's for Adobe. Cause that's what.
But it was just out of curiosity for them.
No. So the other issue, I never had, but again, I've seen people, different ports, different processor. So then you go to so after you select, then you target hardware resources. You go to the external mode and you just double check the SCI, the serial port, right? And just go to your device manager and make sure that it's on the serial port. Again, I never had this issue, but I've seen that some people have. So we add this. So basically, you don't have to do anything now that you have the hard. If you want to do the controller hardware in the loop, then you have more settings, but you don't need that. But if you're interested, you put the module in there, it counts. All right, then you just apply, okay, and then you just treat this as a Simulink, right? So you go to the library, and you just so embedded coder, and you see all the different platforms that they have.
CQ1000.
So as you can see, they brought all the blocks that you want, at least from what I could see. So here, then I always open up the manual for the kit, right? So one thing that you want to know, okay, what are different components, like interfaces that's available, what's the pinout, etc. And now for the communications, basically you can define your own But basically what they have provided, they provided some LEDs, right, that it can be assigned to certain pins, right? So the first command that you have, as I said, you can basically say that, okay, if it's high, then turn this on or off, right, depending on how this is configured. The only thing that you have to do here is just a digital, so you bring in a GPIO digital output, right? So you bring in a digital output, and when you go and you want to set it up, so you see that this one has more than 100 pins, right? So which one goes there to some of the LEDs, you can just go and so you see this one, I think is GPIO, no, is that it?
D1, D9, and D10.
Just make sure. This one, yeah. So this is like a output, so you see like GPIO 34, right? Goes to a red LED or D9, right? And you see the label, and then GPIO 31 is going to blue, right? So now you brought the output, digital output, so red, right? So red is GPIO 34, so you just select GPIO 34. And for the blue, GPIO 31. So if you see this, right? So basically when it's high, this is not conducting, it's reverse bias. When it's low, you have. So in other words, it's active low. So if you want to follow the commands that you have, like when it's high is on, you may decide to put it in there, right? So now I just put constant, but now it's your simulink. So you can bring in actually different sources. Let's say you want to blink this, so I bring in let's say a pulse. So you can actually bring a pulse, or you can do this. So that part is clear. So that's the benefit of that. Just imagine that in your controller, right, you had all of these components, multiplication, different sources, right? You just have to define the interfaces required from this guy, right? So I don't know, as I said, I don't know how Shu taught this, but did he go through this process?
The GPIO, yes, but he also would use some of the macros that were inside
Good.
this.
Yeah, I assume, yeah.
I don't know how much block diagrams for one do. I think it was a lot.
More coding, maybe, yeah. Yeah, as I said, I assume that nobody knows coding. That's the reason for this course, right? Especially for senior design, you see that nobody knows even the spec, so we have to come with the spec.
Would it be acceptable if we were to turn our code in with C++ instead of MATLAB?
Of course.
Okay.
As I said, my students
Okay, just wanna make sure.
don't follow this. But basically, we cannot accept that somebody said, I don't know coding, so I couldn't configure, right? So by this time, I assume that every team has submitted their Simulink, right? So we are just using Simulink instead of just simulation. Now we brought in hardware, so we just make the setup. Okay, so that's that. The next is the PWM. As I said, if I bring in the so I haven't checked the actual resolution of the GPIO for this particular one, right? But as I said, if you don't have much constraints in power electronics, for PWM generations, we go and set up our PWM channels. It's so important that we know that it has the best accuracy that you can get compared to your generations, and I put it in the GPIO, regular GPIOs. So now, for TI, so I think for different platforms may be different. Again, by the way, I wrote all of this, like other manuals in more details. Again, you don't have to turn in these things, but basically you can, for these 4 modules, you can just go step by step, and you're able to do that. Okay, so this one we have done that, so let's go to our PWM. So the idea behind the PWM generation is basically you're trying to generate a controlled waveform or a pulse basically, that you can define its period, right, and the duty cycle. So still we're talking about the logic signal, so the amplitude is not important, so it's still low and high. So one way to do that is basically you have a periodic waveform, right? And then compare it with a reference value, okay? So in this case, you see that your waveform, right, is a triangular waveform here, and your reference is just constant. So now, one way to generate a pulse is by comparing the, basically we call it a carrier to the reference, okay? And you can, in one version, you can say that when the reference is greater than my carrier, right, it would be a high signal, right? So basically you have a comparator, right? So you can do that in complete analog fashion, but again, setting it up in a microcontroller, again, you can write a code for it, but it's so common that microcontroller basically put a built-in block, and you just have to define what you want. So for instance, you may want to reverse that logic that I mentioned, right? It's a comparator, or instead of having a triangular like this, right, you may want to have a sawtooth type, right? So depending on that, basically you have to make sure like what you want in the output. So each of them has its own benefits, right? Especially in power electronics, because sometimes your ADC is synchronized with this, and different points here may represent some points in the output that can be useful to avoid switching noises. But right now, we don't really worry about those things. Any question here? We're good? All right. So with that, basically the next is how do we do this comparator in microcontroller? I'll show you. But the one thing is, in microcontroller, because everything is digital, to do this, we have to count based on the resolution set by the microcontroller or software clock. So basically, if you have a slow clock, right, basically your count would be different. So in other words, if you clock this at 50 megahertz, right, so basically your microcontroller would basically count, right, and once it hits this value, it's changed its output, right? So for instance, in this case, if you want, let's say, I don't know, 20 kilohertz, right? And if you have basically a triangular waveform, right? So basically 20 kilohertz, your sample is 50 megahertz, right? So basically would be 50 megahertz divided by 20 kilohertz, which is 2500. So basically if you count 2500, each at 1/50 megahertz, right? So you have 2500 points to count. And then if you want 50% duty cycle, that count would be half of that, right? So that's really how we do it. In the closed loop, you don't have to actually do this because that's already set up and you have to come up with that number through your closed loop. Okay, so basically in this case, you bring in PWM block from the same EPWM here. And you see there are many tabs to basically set. Okay? So in the EPWM documents, basically I went through each of them and I give you a basically exact setting, right? That you make sure that it should be like this. But I will go through once and I prefer that you do it yourself, see if it's not working and then come back to this, because I think that's more effective. So you do this. So the first thing is so you see that you have EPWM A and B, right? So each PWM channel here, it has its own signal and complementary of it. So for half bridge, for one leg, you have two switches, right? So you set one of them and the next one would be the complement of it. So when that is high, the other is low. So now you have two legs to make a full bridge as an inverter. So basically now you need two modules and you have to set it in a complementary manner. So the important things here, you see like the period here, as I said, if you want like, depending on the type, you know, like counting mode, up, down, you know, or reverse. You can go to help see what are the options in MATLAB. So basically we set it at 2500 and depending again on the shape, it can be 10 kilohertz, it can be 20 kilohertz. So basically I always go and check the scope. I don't go up after theory. So I started with the theory here, but I double check what it actually generates in the output. So now you will say, okay, 2500 is the initial, but do you want to make it fixed or you want to change it output? Here you can define input port or just put the number here. I think the rest, that's true. So counter equals to 0, so that's a synchronization. So here, basically, for up count, so that's you set your comparator that I defined here. Right? So here, you're saying that, okay, when this goes, reach to this, it can be either set or 0. So in this case, I say that, okay, so for the first channel, when it hits your counts or defined counts, clear it, make it low, and when it's down count hit it, right, basically set it, make it high. So for the other one, as you can see here, right, is also doing this, right? But the complementary manner. So you set your counter, right? How it should be set. You have two, I don't know if we talked about deadband, but I think we talked about when two MOSFETs are connected in series. If you set the high signal to both of them, it creates short circuit. So here, same, basically you count, right? Basically turn your time stamp into basically the number of counts. So for instance, if you're looking for 100 nanoseconds deadband between the top and bottom switch, you have to make sure you want to see, okay, that 100 nanosecond is basically what's the count number of that. So if you have again 50, like 50 megahertz, you have to see that, okay, if you set it at 10, what that number would be. So it's about like 100 nanoseconds. And these needs to be set when you want to make this the reading, and for closed loop that we can do it later. Yeah, I think that's it. So here, as you can see, we said that we want to define it externally. So here I define my basically switching frequency or the period, and here is my duty cycle. In this case, 50%. So you go to your hardware, right? You go to monitor and tune. Just make sure that. So it's basically process that, clear the cache, clear your whatever program you had on the microcontroller, right? And then this becomes your interface to control, right? And you can have it on the scope, or you can basically set some LEDs here. So here, what we expect to see is to control light of these LEDs, red and blues, the 8 and 9. And then we want to see basically the PWM outputs. So I don't know if you guys can see, but basically clear now. So now it's processed, the code required, it's automatically generated and dumped into the microcontroller. Is there anyone that haven't downloaded the software for the microcontroller? Everyone started or no? So we need, so I think again, so everyone has the manual, right? So basically, for every module, I think we put some instructions. Just make sure, right, that you go through the user guide installation. So what is required? I think 3 or 4 packages are required so that you can make this. Obviously, there are something specific for TI, right? Remember, Zahid? So you have the code composer, then you need a target for this.
And for this
As an app.
Or you also need C2000ware, which.
Oh, C2000ware, so yeah, so 3, right? So we gave you like step by step, but again, we cannot keep up with the versions, right? So just make sure that you do your own adjustment.
When you try to install this on the CBD for the first time, it already recommends a version. So try getting that version, otherwise it runs out of compatibility. It has
Okay.
issues.
So as you can see here, I don't know if you want it closer or not.
You guys have-
So basically now, you just have to make. So here, what type of probes are these? Is there settings for these probes?
This one should be at 1.
Because this is 40 and this is 2.
Oh, we could check this on quickly. Yes.
Okay. So I just want to make sure that everything is the same. What's the frequency now?
We can quickly check.
What's the?
It's 20 megahertz, 20 kilohertz. Apologies.
How do you say that?
It's 19.9999.
So you have the measure, right? So now look at this. So basically, so we put.
We could just write to that.
So you see now the red is on and there is no blue, right? So now I can turn this off, right? So it's off. Now you can make it on, right? Yeah.
The waveform that's on there, that's the block diagram at the bottom with the EPW9.
This is the, yeah.
Is that the same, that's not the same as the modulation index that we're supposed to do?
Yes.
It is. I think, I don't know, the settings were different, mine didn't look like that.
It should be look like this, but if it's sinusoidal, right, it's changed. This is just.
Yeah, there's a constant, yeah, 2500.
Right?
It's more like-
Yeah,
Yeah, that blocks the constant blocks.
Then running into the internet registry.
So I think with these two, you should be good for your 5-in-1.
It looks like that's the timing ratio, right? TBP. What is TBPRD? The 2500? What does that stand for? Timing block.
Period.
Okay, that makes
So
sense.
basically like the period of the.
It's a scaler
like
for
this,
our
right?
megahertz, right? Off
Right.
of the actual. Okay.
So it will also be time.
So basically just think about this, right? So right, so this has 50 megahertz clock. Okay. So basically, if you count 1, right, is basically 1 over 50 megahertz.
Right. Yes.
So how much is that? Can you calculate?
This one's from the lab.
150 times 2,500. Once every 0.2 of a second. He's got math. Something like that.
Right? So basically that's your step, time step, right? Now you want, let's say, 20 kilohertz. So you want 20 times that number,
Okay, that makes sense.
right? So that gives you this,
Perfect.
right? So you want to count this much because now your unit of measurement, right, is basically your clock, right? So basically 1 clock is this number, 2 clock, 2, right?
So this part right here, is this demonstrated? This would be what, exercise 0?
Well, let me just make the position. So the other thing that you guys have to notice is that they are complementary. Right?
Yeah, so like
Right? So when one is on, the other
The
should
other
be
is off.
off, right? So when you set your EPWM channel, right, just notice that. So if you go up and one you set it as clear, the other one
so for
should
the
be set
EP
as
that we
high.
have, anybody how would you do that? You would write to that registry, and you would have to like. So
Yeah.
for
So what
this
we'd have to do
demonstration right here,
is we'd write that
which
register and then we'd
exercise
do
would
like a
this
for
one
loop that would wait
So for
that
this one,
number
there's
of
no
times,
exercise.
and we'd use that
right?
with the
So
actual clock
basically,
cycle.
you
So
have
the
the
number of
manuals
cycles,
for this
basically the
one,
same as
but
the
there's no
2500. Remember we did
2.5.
that?
okay.
But
It's
this
not
is
the efficient way of
required
doing it,
for
but it works.
5.1.
Right?
So
If we know what
Because
if we
in
know
5.1,
what
You got
what
to a
need
point where
do
this
is
produces the code.
you have to basically operate
it's basically the same idea as what we're doing
right? So
embedded.
previously you had the maybe function
Now with
generator,
5.2
now
we're gonna have to do a
creating your own
PID,
function
so we'd have to figure out the math,
generator,
put it in the
right? So you
code.
want to create
But
this
it's
input to your
I
power
like it better than this,
console,
just because I
right? So-
constantly fight MATLAB. It's the only reason. This is probably easier, but I'm just tired of fighting MATLAB.
Yeah, so,
So
on the
look
desk, those pins.
Start with the LED. So LED is the simplest
Now we
one
have
to
to keep
set
in
up.
mind, what I was reading
So
is we have
basically build
12-bit
this,
and 16 bits.
right?
I think
Just
I
that.
said was 12-bit ADCs.
The reason I'm
So
saying
we have that
is
size
this,
of
there is no
register.
setup. It's just you set
So that's what's gonna
the
sample
what
it.
port and the
Yeah, so the
on the
resolution.
GPIO you
So
want.
we basically
In this
read
case,
from that
Right.
register, and then we'd have to process it, and then
You see?
output
So you
how we want
just
to control
GPIO
the
34.
converter. Essentially,
But
that's
with this
what we
one,
did before.
in
with
this
the
exercise, or what you will find is basically you understand that you downloaded the right software, you know. So this exercise gives you make sure that your setup is correct.
So for
Right.
this is just for the blinking the LED. You're just showing
So for
the
LED,
waveforms.
you don't even need the scope. That's what I'm saying. So just stay at, by yourself. Even don't talk to your friends. Just make sure that your
LED
system is working, right? All the software and whatever, right? The PWM you need to scope,
Question: do we have to use this board?
of course.
We can't use a different Texas Instrument board that we already have.
can.
Oh, okay. Okay.
Yeah, it doesn't matter.
Doesn't matter. Okay. I just want to make sure. Perfect.
But we already bought, so you don't have to buy.
Oh, I have my board from
Yeah,
embedded.
from embedded.
That's the only-
Embedded Bible from embedded.
What is that?
It's a Texas Instruments FR2355.
Well, the only thing that you have to make sure that MATLAB supports that,
Of course. Of course.
you know?
Okay.
So that's the only thing. So the message here, everything now becomes like your Simulink, but now you bring in the hardware in the loop, basically.
Excellent. Excellent.
Because I remember when we were looking at the documents, it's like what, 2 Word documents and 2 PDFs, and it's like kind of like
There's 4 documents that we had.
and those are like
And then
which
there's the
one-
main document that it comes with.
Yeah, so just saying like which one, like which of those documents you want us to like look at first. Like, start off. That was my question. Basically.
So what we did is we had issues finding it, so I went ahead and searched Canvas and then downloaded the file names that were inside the main file. But I think we need to refer back to the main file. And that kind of gives us a little bit of an order.
Yeah, because it says
But it
like
is-
reference this document and stuff like that, and then like in that document was first like another one. Just it goes like so that kind of confusing.
A little bit, yeah. Yeah, I'm just gonna sit down with it after, I got a conference to go to at 5. That goes to like 6 or 7. So after that, I'm probably gonna stay here in the lab and work through it. Just because we need to get it working.
The value of the.
You guys don't
Open
see
lab,
these
I think.
things.
Hey, you got your open lab. Excellent.
Yeah.
Excellent. I don't know
Oh,
why
they
mine
accept the proposal?
automatically worked. I never got access. It just worked.
Oh,
Okay,
wait.
so here
How
it
do you
is.
get it?
You talk to Eddie. But he has to put in a request.
To
Yeah,
who?
Eddie's
Who's
the
Eddie?
manager guy, the older guy who. So you know, between the two labs, there's a door. Knock on that door. You know, during normal business hours, he's usually there. You just say, "Hey, I need access to open lab. I'm electrical engineering student." He'll just ask for your student ID.
Okay.
Yeah. But it takes a while because whoever
Yeah,
does
I
it
know.
is not Eddie now. It used to be Eddie. Yeah, for some people it takes a
So-
day or 24 hours.
so
Some
here,
people it
It
takes
depends
3
whenever
weeks.
you request.
So-
Like Shu
so
couldn't
what
get
I
his
just
class in there,
explained,
and
right?
he's a teacher.
So you can
it took him like
use
3 weeks.
either of them, maybe this
Weird.
one. Okay. So this is set at 20 kilohertz. So this is to generate EPW. To start with, go with SCI.
Start with
Right.
SCI,
So
perfect.
these two should be sufficient. You have to do the modifications to make the sinusoidal if needed for the 5.1. Right now it's just constant,
Perfect.
right? But I assume you can just bring in sub-constants, bring in sinus waveform,
Okay.
right? So these two modules are good for that, and then closed loop and ADC setting is for 5.2.
Okay. Gotcha.
Okay, but yeah, these are I suggest everyone just do this once.
In terms of probes, you had an issue. Does it matter what probes we use?
No, it's
No.
just like Rahim basically
We configure the scope of work.
configured this for this project.
Ah, understood.
Yeah, so the scaling should be the same.
Okay. Yes, of
right,
course.
What you see.
Got you.
Well, I know what I'm doing. I'm gonna experiment with my board in
All good?
C++. Yep.
I wonder if I get another part.
You want to get another one? Get one that has a display so you can have some more fun. This one has a display on the back of it, I think, like a port for it.
And then
I think
basically
it's definitely a ribbon cable.
the Simulink is perhaps is harder, but looks harder, but essentially 5.2 is that you bring in the ADC module. Basically,
Yes.
that sets. Just have to set like what I did for the LED. That's okay. Read the signal, right?
Yes.
You just have to set it. Then you want
Read
to
the
say that
register.
okay, do some function multiplication.
That's the
In
hard
your
part.
code, you
That's the
need
hard part.
PI for just the class. I didn't even put the PI to just see the basic, right? So just the gain, right? So really, I mean, the next lecture is there. So we really want to make it like a technician, right? We want to use this, and we want to make it work.
So if I wanted to do that in C++,
You have to write down.
I would have to write out the math for the PID.
Again, you don't have to write, right? You
Okay.
have to follow your microcontroller,
Of course,
right? How
of
to
course.
set up my ADC, right?
Yes, that is fine. It's a
You know?
question of
But if you want to
The
write
PID.
down like the algorithm, like okay, I multiply, subtract, that's the code.
well, that's arbitrary.
Right.
Yeah.
But here you don't even need to.
Yeah. So we'd have to just set up a clock and then do. Yeah. Okay.
All right.
Yeah.
All right, guys. Thank you.